Hi, we will demonstrate here how to run on the ROS the demo machines of the MyPal lab. So we're assuming that you are familiar with ROS core and that you can also run the turtle simulator. So now we're gonna download the compiler of logic label finite state machines. This compiler can be downloaded from the MyPal Machine Intelligence and Pattern Analysis Laboratory in Downloads. So you just come here and the whole package will come down. We save the file into our Downloads folder. And so we can, if I do list after saving it, is there. And we tar extract the file CLFSM. So we just go into it and we say cat make, and this will compile the two libraries, the whiteboard library and the CLFSM library, and leave us an executable of CLFSM. So if I now look at the bell lib, you get to see here the executable for logic label finite state machines, the library for it, and the library for the whiteboard. If this not succeed, is maybe usually because you don't have libdispatch installed. You can have a look at, you install it usually the standard way you install packages in Ubuntu. Executing a very simple finite state machine. If you look at the documentation, it looks like this. It's a machine that will publish the string hello world, wait for 10 milliseconds, add into a counter, and it goes back after 10 milliseconds and publishes again. Alright, it has an initial state to configure the ROS topics, and so that's where the machine will start executing. After 1,000 milliseconds, that is after a second, it will start iterating. If at any point in time ROS fails, it will go to the end. The end being the state with no transitions out will decommission the machine. The execution will stop. That's the intention of demonstrating this. So we're gonna demonstrate this execution. So the first thing to do is go again to the downloads page, and all the demo machines come up from this file. Before we had an entire workspace, now we're going to incorporate little by little these executable machines into the workspace. So let's download this. We're going to save it as well. Alright. And I also already downloaded the documentation, so that's how you saw that I have the PDF here to, in the video, show the machine a little bit larger. So we go back to our downloads folder. You're going to see that we have now here the demo machines. So we're going to do it step by step. So as you can see, I'm just unpackaging the compressed file. So after that, we have a tar just here. Alright, so now I extract it, and these are the demo machines, and as you can see now I have these machines here, 3 of them. So the thing is, we're gonna incorporate it into the workspace. So I'm gonna go here into the Catkin workspace, and I'm gonna go into the source component of the workspace. So we're going to add the package to the workspace. To do this, the documentation already here at the bottom, so I'm going to do it from the website. Here's how you create a package for the ping pong machine. Grab it now, copy it, and inside the source we create and it's important because you see here the dependency to LCFSM and CLFSM. So now we have our ROS ping pong package where we're gonna host the machine. The way to do that is, besides the normal things that a package has, like an include and a source directory, we're gonna do a machine directory. Alright, and in this machine directory is where we're going to host the machine. So the first thing you want to do is bring all the machine over to this place. So if I go just back to our downloads, alright, remember what we just download these machines, alright, and I'm looking at this ROS ping pong. Although it's already the whole structure of a ROS package, I'm going to do it step by step. So you see that this machine directory is here. So if I go to machine, alright, in fact a logic label finite state machine at the moment is nothing more than a directory which has all the states that need to be compiled. Some of them are the code, some of them are headers, and so on. Some of them are expressions for transitions. So basically we need to use a shell, a script, to break this into a format that CAD-can-make will build the CMake appropriately to compile all these files for CLFSM. So what I'm going to do here is actually tar it. Okay, so I can bring all those files together. Alright, and this is from the place we download. I'm moving it to the package. So as you can see, I'm now in my package that I just created, and I'm gonna move from downloads, machines, ROS ping pong, machine, ROS ping pong, the tar. I'm gonna put it here. This is essentially moving the code into the robot. You can think of it that way. Alright, and then I tar and extract it here. Now I usually have the discipline of removing my tar file so I don't get confused between which one I'm running and so on. Now in the MyPal Machine Intelligent Downloads, there's a script that we're going to download as well. Save it, and this is going to be the script that does most of the setup for a machine. So it should be now in downloads. As you can see, it's here. Alright, we're gonna move it to this place. So from downloads, I'm moving machine CAD-can setup here. I'm gonna decompress it. Alright, and then I'm gonna just make it executable. So now if you see, it's in green because it's executable. So we can run it with a machine. And this will create a whole CAD-can infrastructure for compiling a machine. It will give you a suggested CMake list file. What we're going to do is go to the CMake file of the package for the machine up and copy the dependencies that you see here. Alright, so I'm going to do explicitly an edit copy. Exit my editor. I'm going to suggest it, and I'm going to delete, because the script does not know all the dependencies. We created the dependencies when we created a package. All right, and now that the suggested CMake list, if you want to look at the suggested list, it's okay. You're going to see that it details how to compile every state and every transition. All right, so we're just going to copy the suggested one level up to the CMake list file. We just went one up. All right. And that's all we need to do. So let's compile the machine. How do you compile? With ROS, you go at the top level of your workspace and say CAD-can make. And you see here compiling different states of the ping pong machine. Alright, so let's execute it. Let's go to the bell. Alright, lib, and the machine gets compiled as a library. You see it here. This directory is built up by the script, by the setup script, so that CLFSM can find the machine. Alright, so but we need to move that library. So you see me copying the library to ROS ping pong, and because we compile for Linux, now the only trick here is that you have to remove the lib from the front of the name. Move that, okay, and now we are ready to execute CLFSM. I'm putting the -V option for pause so that we can see how the machine iterates through their steps. I don't have ROS core running, so I receive an error, so I'm going to go to another screen, get ROS core running, and when ROS core is running, you can see here the machine. I'm going to kill it for a moment so you can see the states and also how fast it went running from one to the other every 10 milliseconds, printing a new world. Okay, you got one machine running. Last scene, you saw a machine executing, so we know it's going to do a second machine. The second machine also has some initial state to set up the ROS node that represents the machine. After a second, it's going to change the parameters of our turtle simulator to go straight. Then after a second, it's going to make it do a turn to the right, and then another second to go straight. And it will go there as long as the ROS environment is okay. So we're going to run this machine. The process is going to be very similar as before, right? We need to create the package, all right? So I have another window where is the downloads. Remember that the machines are in there, so in our downloads we not only had ROS ping pong, but we're going to have a look at the second one that we downloaded, and we call it blind because it doesn't use any sensors. Alright, so I'm going to copy this, and remember that here we created a package, and because it doesn't need any sensors or anything like that, we're going to go into the source part of our ROS Catkin workspace. We had already this machine, so somewhere in my history I have the create package, so I'm doing all the way here to create the package, and we're going to create it exactly the same way, but now it's going to be the second machine, so we have a second name there, ROS blind turtle pot. So we create a package. When we create a package, we have it here, and again, for finite state machines that we want to run, we go into the package itself. Basically it's empty. You could update, like in the tutorials tell you to update the package.xml and so on. Remember, we're going to replace the CMake list on how to compile. So in order to do that, we do a directory called machine, and in this directory, right, one of the things we're going to need is our setup script. So I can copy it, machine setup. All right, so this is the script that created the suggested CMake list file. So remember, we're going to replace this guy by the suggested one. So I'm going to bring the code of the machine from the download. So in order to do that, I'm going to go into ROS blind turtle bot. I'm going to machine. All right, and here is the code of the machine. Remember, every machine is really a directory with lots of states, transitions, and expressions, all separated. Well, they're created by editors. If you use my edit, we will help you create these files and separate everything in the correct place. So at the moment, what I'm just going to do is just, in order to copy it, put it into a tar. So, right, and since we created the tar, I can go back to the place where I'm going to build it. Right, and remember what we did. I go from my downloads, machine, ROS, blind turtle, machine. I'm going to move the corresponding tar file. So now I have the tar file and the script. I'm going to extract it here. This is like extracting it inside the robot. This could be, of course, automated with a script. So now I have the machine here. I'm going to remove the tar just in order that I don't get confused with. You can also make scripts for this, or it probably should be part of the setup script. Let me just remind you that this script will create a suggested Alright, you see here the suggested. So we actually take the dependencies from the proper CMake list. I usually do just a select and open the suggested one, and this will get, with the term machine you would see more the purposes of these things, and then I copy the suggested CMake list into the actual one, going one level up. Okay, and now we are ready to compile this machine as well. Alright, so remember in the Bell lib we only had CLFSM, the very first two libraries. We had the machine that we compile, and we have now ROS build turtle.machine because the setup script created that for us. But with Quadkin make, we compile this second machine you're seeing here in the background with those three states. It's compiling the state initial. Alright, once we're done, we go into the Bell lib, and now we have Blind Turtle as a loadable library compiled for us. We still need to do that little step of copying it into the path that CLFSM exit to be, and we have to copy it without the, so there it goes, and now we can run CLFSM -b, and we will run the machine, but I'm not going to run it just yet because I want to see the effect on it. So remember, we need to have ROS core running, and because I want the behavior to impact on the little turtle, we're going to have it there. Maybe I move here this for a moment so we don't miss what the turtle gets doing. And as you see, it goes straight for a second, turns for a second, goes straight for a second, and you continue there forever. You can see with the -b option, CLFSM tells you machine 0, state 0, machine 0, state 2, state 3. So by now, it's just jumping between symbolic names state 2 and 3, but you get the name of the state here as well. Alright, a machine that operates the actuators of a robot. Very simple, but you can make a robot do something. We're in a position to demonstrate the execution of the third machine that we see here. So this machine will react to objects in the environment. In particular, it will walk away from the wall of its environment. So we're illustrating the first aspect of sensors. The previous machine, in a sense, mentioned effectors of actuators, so we could control the robot moving. Now we're going to sense things in the environment. The other aspect about logic label finance this machine is that you can see here they're always running. They are code that runs, and then after a certain amount of time these runs, and then after a certain amount of that these runs, and then transitions gets evaluated. Actually, we see another transition going out this way and another transition going out this way. So they're always running. You cannot have callbacks. You cannot have an event start another thread in the machine. So in order to operate a sensor, these machines are going to have to ask for a service. And as you can see here, these services, a service we're going to build to request the position of the turtle from the ROS environment. If that position is not too close to the wall, which is this situation, it will go back and continue to move straight. However, if the position is too close to the wall, it will back up for a bit. Alright, and then we'll go here, and then we'll escape this way up and continue to go straight. Alright, so if this is not true, after a certain amount of time, it will come around this path and turn around from the wall or from the obstacle if it gets too close to the obstacle. So typically with ROS, that means that we're going to have to create an extra node that if something is published in a topic, and unfortunately the turtle position in TurtleSim is published in a topic, we're going to create a node who listens to that topic and is ready to provide a service, which will be the service we're going to invoke here to retrieve the position of the turtle. So that service also comes down from the MyPal downloads, all right? And so we call it here the turtle sensor poster. It's already a package. So we're gonna bring it down. We're gonna save it in our downloads area. We go back to the place where we are working with downloads here. So this is a window that we're working with downloads. All right, I'm going up to the downloads place, and we have the turtle sensor poster. So all right, we untar it. All right, I invite you to explore the code of this turtle sensor poster. As you can see, it's a package. All right, so if I look at what's inside of this directory, it has an include, and it has a service, and therefore it will be able to provide this service. It will listen to the topic about the position of the turtle and provide this service. So what we're simply gonna do, all right, is go to our workspace, go to the source, and I'm just gonna move from downloads the whole package, turtle sensor poster. Let's just double check that is what it's called, and I put it here. So now I have that package as well here, and we're gonna compile with cat-can-make. Cat-can-make checks if there's been changes to any other packages, compiles the turtle sensor poster. Just for reference here, all right, I'm gonna open a new tab, and we are working, remember, in downloads in the workspace, Calcan workspace, and I have at the bell, all right, and live, and now I'm gonna have as an executable, I want it to go into live, I have as an executable also the turtle sensor poster. So that's like turning on the sensor. So let's do the new machine. The new machine is a bit more complicated because it's going to precisely depend on this part. So if you look now at the or documentation for these demos, you're going to see that this is the general format to this line here gives the format of how to create a cat-can package. Well, for the third machine, we want to show that it also depends on this turtle sensor poster that provides a service. So if you go down here, the documentation, all right, we're looking at the second machine in the documentation. This is very detailed about how we build them, what's in each state. You can see here the difference between the fact that subscribe are usually a mode where we use callbacks. Machines work basically with a get messages. Logic label finite state machines basically on a get message approach. All right. So here is this machine as we're gonna. Here it explains this part about the turtle sensor poster I just briefly demonstrated. And I expect to see here in the documentation how this is all the explanation of what happens inside each state, all right? And it also tells you that we're going to use the machine setup script, all right? So all that is very similar as before, except now, as you can see here, to create the package, we're going to add the turtle sensor poster at the end. All right, so this machine, its execution depends, or we want to emphasize that it depends on the turtle sensor poster. So remember that we go to the source. Somewhere here in my history, I should have the create package. But now the first thing is we're going to create it with the name of the new machine. The new machine is now not Sublime. All right, so if we look at machines that we downloaded, the new machine is called TurtleBot, and so we're gonna put it here. And besides, depending on all these, it also depends on the turtle poster. And this shows you why it's impossible for the script to set the machine it suggests to you what are the dependencies, but it doesn't know it from scratch because it depends on actually how we create the package here. Alright, so if we look at the packages that we have so far, now we also have the Roswell wall turtle boat. Everything is pretty much the same as we did before. We don't have a machines directory, so we make the machine. Alright, we go into machine and then we copy from, let's say, Ross line turtle boat machine, the machine setup shell, and this is the shell that, as I said, doesn't know all the dependencies. That's why it only suggests you the CMake list file, but it cannot do everything. So we go here now, we're gonna move the machine again. So we're gonna go to Roswell turtle boat machines, and again, to bring it all, I prefer to tar it. So alright, so I'm moving my source code by tarring it first, and then here, once I have it, I'm gonna move from downloads machine, Roswell machines, Roswell tar. This is like moving it to the robot. Then I'm gonna extract it. Alright, now out of discipline, I remove all the tars here. Okay, so I don't get confused if there's updates to the machine. And now we do the machine setup. And let me just show you here that I don't have that .machine file yet. This machine setup, besides doing the creation of the suggested CMake list, is going to create the folder here, the directory. And that's all we need now. So we go up to the root of the workspace and cat can make to compile this machine, this last one that we have here. Alright, so now if I look at what we got here, oh, I didn't copy, so there you go. We go back to Roswell. This shows you the effect machines. Alright, and I didn't do that step that I was talking about. So if you look at the suggested, it does not have the dependencies. So this shows you why are we doing this step. Here's the dependencies with the turtle sensor poster. So we copy that. We open the suggested. So if this happens to you, that your machine didn't even got compiled, is because we have not copied the suggested CMake list file into the actual. Otherwise, we have an empty CMake list file. The suggested one was created by the script. Alright, so we go up here. We say cat can make. Now it's compiling the machine. You can see some of the states here being compiled. And so now when I look at here, I have the machine compiled as a library. And I also, the setup has created a directory in which I'm going to copy that library. So I'm going to copy live Roswell into Roswell because we compiled for Linux. And as I've been doing before, in this particular case, we do not use the live at the front. Alright, we're almost ready to run our machine. So it will be CLFSM, CLFSM-B, and Roswell machine. But before we run it, we need to start ROS core. We're going to start the simulator, the robot actually doing something here. Alright, and now the next thing we have to do, I'm going to open another tab and run the turtle poster. So here you get actually to see the position of the turtle. Alright, and so we run the machine. And you see the robot that walks forward when it gets too close to a wall, backs up, turns up for a bit, keeps on moving, goes forward. All right, if it gets too close, backs up, keeps on going straight. It'll make it go here so you can see that it gets very close to the wall here before it decides to go straight. So you have now a machine that controls a robot, which can sense aspects of an environment, and you can not only make the robot move, but behave according to sensory information.